Okay. Uh, 3.9. Related rates. Related rates. Let's think of a following scenario. We pump air into a balloon. So we have it right here. It's empty. Doesn't have air in it. So now we pump air into this balloon. What happens? The volume definitely increases. Would you agree? What else increases? You can say the surface area. I agree. The surface area will increase. What else is increasing? The radius will be increasing, right? So the volume, the surface area, the radius, they all increase. The derivatives, the rate of change, in other words, of increase for the radius, the surface area, the volume, they are related. First of all, they happen at the same time, right? And the second thing is they are related in the sense that when one is 5x, the other one will be 5x squared, as an example. So there are so many different applications here. I don't even know what to start with. But I would like to start with 27 on page 249. So we see how this works. I think you're going to enjoy this. Gravel is being dumped from a conveyor belt. And we are given a rate, 30 cubic feet per minute. I'll stop reading the problem, and I will ask you, what does this mean?
So it's 30.
Right. So if I say that gravel is being dumped from whatever onto a spot at the rate of 30 cubic feet per minute.
Isn't it like 30 feet cubed?
No. Cubic feet per minute is just the measurement unit, has nothing to do with 30. It's like I tell you, right? What does this mean exactly?
Represents the rate
of change of volume with respect to time. Very good. dV over dt. Because the measurement unit is cubic feet per minute, and because I know that any rate of change or derivative for a particular real-life situation, not abstract, in other words, has a measurement unit for the top. This is the measurement unit for the top. This is the measurement unit for the bottom. So when I'm given 30 cubic feet per minute, I know it's dV over dt. What if I were given 25 square feet per minute? What would you consider that? But it's not, I said square feet per minute. The area over dt. Yes. What if I'm given something like feet per minute? It's the rate of change of length, dl over dt. If I'm given cubic, it's definitely volume. Good. Okay, so let's read on. It's such that it forms a pile in the shape of a cone. So it forms a pile in a shape of a cone whose base diameter, this base diameter, and height, this, are always equal. I'm going to call the height h. I'm going to call the base diameter 2r. So this is twice r. And I'm told that at any point in time, h equals 2r. Remember when I gave you that example with the balloon, the surface area, the radius, and the volume, they all change, and they change at the same time, and there is a relation between their rate of change? Well, we can't have three variables because this is single variable calculus. So we can only have at most two, and there must be a connection somehow, so we can differentiate, because we don't know how to differentiate a function with two variables at this point. So let's read on. How fast is the height of the pile increasing when the pile is 10 feet high? What am I asked to find? How fast is the height of the pile increasing? I'm asked to find the age over dt when the height of the pile is 10 feet. Exactly. This is what I'm asked to find. This is the question in the problem. So we know that we are dumping, what are we dumping? Is just, what is it? Gravel. Okay. We're dumping gravel here. We are creating this cone. We know that the diameter, the base of the diameter and the height will always be the same. And we know that the height is increasing, the diameter is increasing, but they increase at the same rate. And the volume is given, it's increasing at 30 cubic feet per minute. We're asked to find how fast is the height increasing at a particular instant. What did we say a long time ago when I said, find f prime of 3? I say to you, please find f prime of 3. What will you ask me? Give me f, right? Give me f, I'll find f prime, and then I'll plug in 3 in it, correct? So what will I have to find first? A function or an equation that gives us what?
Volume of
the height. So somehow I have to find an equation for the height. Second step, that's first step. Second step, I have to find what? The derivative of that. And what will be the third step? Plug in 10. So please remember these 3 steps. You cannot, don't erase it like that. You cannot even think of this. Don't even mention it till you have the function and you differentiated it. You cannot even talk about this. This does not exist. So this happens after I find the function and after I differentiate it, then I plug in 10. Till then, don't even mention it. Okay, wonderful. So where is my starting point? Well, based on what I'm given, no, we don't have anything just yet. Well, if you want, yes, I have this. But that's just a piece of information, that's just a detail.
Isn't that like a cone equation?
The volume of the cone, of course. Very good. So the volume of the cone is easy to remember. Remember the volume of a cylinder and put 1/3 in front of it. What is the volume of a cylinder? Area of the base times the height. What is the area of a base of a cylinder? It's pi r squared. It's a circle. Area of the base times the height with 1/3 in front. Since I'm asked to find a function for h, I will solve this for r. Because see, I have r here and I have h. I have to get rid of r. Because I'm only asked to find something for h, not for r. That's why I'm given this. So from here I'll say, or write r equals h over 2, and I will replace it in here. I can only have h and v. I cannot have more. So r is h over 2. So v equals 1/3, or pi over 3, multiplied by h over 2 squared times h. Finally, v equals pi over 3 h cubed over 4. H squared times h is h cubed. 2 squared is 4. So one more step. Pi over 12 h cubed. This is what I need. Since v and h are functions of time, I have to differentiate the left-hand side and the right-hand side, keeping in mind that v and h are functions. So please differentiate the left-hand side.
dv dt.
Very good. dv over dt. The right-hand side. pi over 12 times
3
times,
h squared
very good, times,
h prime.
yes.
No, dv. H.
So both are functions of time. So the left-hand side is dv over dt. The right-hand side is 3 pi over 12 times h squared times dh over dt. So after all this work, this is what I'm after. I will solve for it first. So I'll simplify by 3. So then I have dv over dt equals pi h squared over 4 times dh over dt. I'm solving for dh over dt. Please tell me what to write.
You get 4.
Oh yeah, you can if you want, but I will just write dv over dt over pi h squared over 4. But yes, you're right. Now I can evaluate it when age is 10. I could have not done this before. That 10 meant nothing. So what is dv over dt? It was given to us 30, then pi, and then 100, and then over 4. So this is 25, then 25. So it's 6 over 5 pi. I'll have to divide that. Six divided by 5 and further divided by pi. I got 0.382. Measurement unit, 0.382. It's a rate of change. It better have a measurement unit that has something for the top and something for the bottom. dH over dt is 0.382, measurement unit.
Feet per second.
Minute.
Minute.
Good. This is one example of a problem concerning related rates. One more time. What is related here? The rate of change of volume is somehow related to the rate of change of the height of the cone as we pour gravel onto it. So these are the two related rates. They are related through this equation. When one is 30 cubic feet per minute and the height is 10, the rate of change of height with respect to time at that instant is 0.382 feet per minute. And this is what we call related rate problem or related rates problem. Ready? Any questions? Any questions? Can I choose another? Okay. Oh, what did I? Okay, let's look at 22. A particle moves along the curve y equals 2 sine pi x over 2. As the particle passes through the point 1/2, 1, its x coordinate increases at a rate of the square root of 10 centimeters per second. How fast is the distance from the particle to the origin changing at this instant? Sounds difficult. A particle moves along this curve. And as the particle passes through this point at this instant, its x coordinate increases at this rate. What does this mean?
dx dt.
Very good, very good. dx over dt is the square root of 10 centimeters per second. How fast is the distance from the particle to the origin changing at this instant? If you want to graph this, when x is 0, sine of 0 is 0. And when x is 1, sine pi over 2 is 1, times 2 is 2. I just graphed it between 0 and 1. Here's the point 1/2, 1/2, 1/2, 1. I don't think that, so x is 0, sine pi over 2. So sine 0 is 0. When x is 1, sine pi over 2 is 1, times 2 is 2. Okay, so I guess you're going to have to trust me that this is 1/2, comma 1. When x is pi over 2, 1/2, this is pi over 4. There's a square root of 2 over 2. Let me see if I copied the function correctly. Yeah, pi x over 2. So when x is 1/2, this is pi over 4, and this is a square root of 2 over 2. And with 2 in front,
Overall,
Point is at 1/3.
oh, I copied the point incorrectly? Oh, sorry. That's why I said the point is not on the graph. What are they doing? Okay. I'm doing this again. So so this is pi over 6, which is 1/2, times 2 is 1. Yeah, I agree with that. I don't agree with the other one, of course. So it's 1/3, comma 1. I copied the point incorrect. Thank you, Eric. Okay, so now this makes sense. 1/2. This is still 2, and this is definitely 2. So this is 0 and 1. That's very clear. I don't know why the point is just, oh, it's 1/3 now. Yeah, that's why. It's right here, of course. It's 1/3 and it's not 1/2. I'm still on 1/2, hung up on 1/2. Okay, perfect. That's where it should be. 1/3, comma 1. And it is, finally, in the right place. 1/3, comma 1. Perfect. So now we are told that at this instant, dx over dt is the square root of 10 centimeters per second. And now they want us to determine how fast is the distance from the particle to the origin changing at this instant. So I'm going to graph it a little bit bigger here. So this is the particle. This is the distance. I'm going to call it z. So this is the distance between the particle and the origin. And they're asking us to find the rate of change, or how fast is the distance between the particle and the origin changing at such and such instant. What am I asked to find? dz over dt. So that's the question. When x is 1/3, but I don't care for that right now. Good. So here's what I'm going to do. I'm going to form a right triangle where this is definitely x and this is definitely y. Y is the same with 2 sine pi x over 2, of course. So can anyone give us the Pythagorean theorem or apply the Pythagorean theorem in this right triangle?
you have x squared
X squared plus
plus 4
4
squared
sine squared pi x over 2 must equal,
Z squared.
very good. So I have an equation that includes z. What should I do to both sides to get dz over dt? Say it again.
Square.
I want dz over dt.
Oh, D0.
I want the derivative.
So then,
Differentiate implicitly. Exactly. That's why this section follows implicit differentiation. Good. Now I have to remember something very important. X is a function of t. So is z. So x is not plain x. Z is not plain z. Z is a function of t. X is a function of t. Let's differentiate. 2x times
X, dx dt.
dx over dt is a function. So x squared prime is not 2x. It's 2x times f prime plus
So 4 times
8, yes, sine pi x over 2 times the inner function prime
over 2.
cosine pi x over 2 times the further inner, yes, indeed, pi over 2 equals 2z dz over dt. Let's do this one more time. X is a function of t. So when I differentiate a function squared, I get 2f times f prime. 2f times f prime plus 2 times 4, 8. Sine to 2 minus 1 times sine prime, which is cosine, times the inner function prime, which is pi over 2, equals 2z prime. I'm after this. I will divide both sides by 2 to eliminate this 2. I have 3 terms, and I'll simplify this by 2, this by 2, and this by 2. And I will further simplify this and this. So, x dx over dt plus 2 pi sine pi x over 2 cosine pi x over 2 equals z dz over dt. And now I'm ready to determine dz over dt as we did implicitly a long time ago. X dx over dt plus 2 pi sine pi x over 2 cosine pi x over 2 over z. Now let's see what we have and what we don't. Is this okay? Is this equation okay? Okay. So now what we are given is x equals 1/3. Dx over dt is the square root of 10. I have to find z. So here's how I find z, by taking square roots from both sides. So this is the square root of x squared plus 4 sine squared pi x over 2. A lot of numbers here. So dz over dt is 1/3 times the square root of 10 plus 2 pi sine, this is 1/3, so pi over 6, sine pi over 6 is 1/2. Cosine pi over 6 is the square root of 3 over 2. Everything divided by the square root of 1 over 9 plus 4. Again, this is 1/2 because it's 1/3, so pi over 6 is 1/2 squared, 1 over 4. Okay. So the square root of 10 over 3 plus pi the square root of 3 over 2 over 1 over 9 plus 1, 10 over 9, the square root of 10 over 3. And no, you don't even try to simplify or anything like that. So I'm going to put everything in the calculator. So for the number, let me do this with this. Okay, so left parenthesis for the top. The square root of 10 divided by 3. So the square root, let me see, I need more parentheses. No, I don't. 10 and outside divided by 3. And then outside plus pi. I didn't mean that. Oh no, I didn't mean that either. Ugh.
You hit delete.
Yeah, but I have to be there. Okay. So plus, it was pi. I meant here. Yes. Okay. The square root of 3. Outside divided by 2. Close the parenthesis. And further divide the whole thing by the square root of 10. Parentheses. The square root of 10. Outside. Divide this by 3. And close the parenthesis. I got 3.58. There is no measurement unit here, only because we're not given any measurement unit. It's all happening on the Cartesian system. So we're not, oh no, I think yeah, we do. I'm sorry. Centimeters per second. I forgot that we were given. We were given the x in centimeters per second. For a moment, I forgot that they were giving us. Oh. Did you check my, I don't trust this software. I trust my calculator though. So, did you check my answer? Anyone?
My battery is
Yes?
dead.
I'm checking with my calculator though. Divided by 2. Okay. And then further divided by the square root of 10. If one of you got the same thing, then I'm fine. Yes, I did get the same thing. 3.58 with my calculator. Okay. Any questions? It's a lot of work in these problems. I hope you agree with me. Okay, 16. There is no end, really, of this section, ever. I can't say that. There is an end. A spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building. So here's the man. I can't draw a man, as you can see. If a man 2 meters tall walks from the, so he's 2 meters tall. So he walks in this direction, towards the wall, at a speed of 1.6 meters per second. How fast is the length of his shadow? Here's the length of his shadow. This one. How fast is the length of his shadow on the building decreasing when he is 4 meters from the building? So when the spotlight is right here behind me, my shadow is big on that wall. As I move away from the spotlight, get closer and closer to the wall, my shadow on the wall will decrease. So what am I asked to find? And what will be the sign of the answer? I'm asked to find?
THDT.
I'm asked to find the age over dt. And that will definitely, for some value, I don't know yet, we'll establish it in a minute, but that will definitely be a negative number, whatever that is. Let's read the problem one more time. A spotlight on the ground shines on the wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of the shadow on the building decreasing when he is 4 meters from the building? So I know I'm asked to find the age of a dt. I know that will be a negative number. So what is my starting point? So first of all, I'm given 1.6 meters per second. What is that? So here's the spotlight right there on the floor, and I'm walking away from it at a rate of 1.6 meters per second. This is the distance that I'm covering. You can call it x.
Yeah, it should be DXDT.
Dx over dt. So this is x, and dx over dt is 1.6 meters per second. Good. So now we know something, and this is your hint. What am I getting at? And how are they called?
Are they ratio?
They will be. How are these two called?
Yeah, similar. I was going to say equal angle.
Similar triangles. Similar triangles. This triangle is similar to the big one because they have a common angle and they're both right triangles. Therefore, we can write proportions with their sides because they are similar. So let's start from the common angle. The opposite of the common angle in the small triangle is 2. The opposite of the common angle in the big triangle is? Good. Now, there is nothing I should write about this. I don't know anything about that. So I'm looking at this angle. What is the opposite of this angle in the small triangle? The same angle right here. What is the opposite of that? 12. What do you think I'm going to determine from here? I have two variables, but which one I'm interested in? Yes, of course. I'm interested in the height. So cross multiply, xh equals 24, or h equals 24 over x. Or better, 24 times x to negative 1. What do I do next?
Differentiating.
Yes, differentiate. Remember, h and x are functions of time. They have to be treated as functions. So I differentiate h. What do I get?
DHDT.
Very good. I differentiate the right-hand side, and I get negative 24 times x to the
Negative 2.
-2 times
x dx dt. Sorry.
dx over dt. So in other words, dh over dt equals -24 over x squared dx over dt. And now I can read on or come back to the question. How fast is the length of the shadow on the building decreasing when he, the man, is 4 meters from the building? So I'm walking away from the spotlight, and I cover the distance, and now I'm 4 meters away from the building. So what did I cover? Because this is the rate of change of x. So what did I cover when I get to this point where I'm 4 meters away from the building? Exactly. So this is when x is 8 meters. I can't put 4 in there because this is what I covered, not that. So this is what I have as dx over dt. So then this is -24 over 64 times. How much is dx over dt? Dx over dt.
1.6.
1.6. Very good. So times 1.6. I grab my calculator. Let's see. 24 multiplied by 1.6, and then I divide by 64. I got 0.6. Measurement unit, please. Very good. So the shadow on the wall will decrease at 0.6 meters per second at the instant the man is 8 meters away from, because at the other instant it will be different. It will change at a different rate. It will decrease at a different rate. But when he's exactly 8 meters away from the spotlight, the shadow on the wall decreases at 0.6 meters per second. These are related rates. So the rate that he is walking with the rate of the shadow changing on the wall, these are related rates. They happen at the same time, and they are related through this relationship. This is the relationship that they are related by. 1 equals -24 over x squared times the other. And a particular instant of x equals 8 away from the spotlight, the shadow changes at -0.6 meters per second. And that's why we call this related rates. And there is no end to it. There are so many different situations. We'll have definitely more examples. And the last section after this is, no, I'm lying. There are 2 more sections, and I have to mention something about hyperbolic functions. So we will look at linear approximations and differentials on Monday, and we are going to look at 3 functions, just 3 hyperbolic functions. Hyperbolic sine, hyperbolic cosine, hyperbolic tangent. That's it. And their derivatives. And related rates. We're going to be able to approximate very, very accurately the square root of 1 over the square root of 101 with no calculators whatsoever, using calculus. We will be able to find a very, very, very accurate tangent of 44 using calculus, no calculator. So I'm thinking a week from Monday, I think we talked about it for our test, a week from Monday? A week from Wednesday?
19th. Yeah, 19th.
Okay. So next week, it's going to be the 10th and the 13th, right? And then we said a week from Monday. Right? I need a session to review all this. So assuming I finish on Monday, which may or may not happen, and we review on Wednesday, then we will have the test the following Monday. Right?
We were saying.
Oh, we're saying the following Wednesday.
Yeah.
Okay, it's even better then.
The 19th.
So 10 to 19, 10, 19. Very good.
So
Yes.
for WebAssign, when I used